So the point of this lecture and eventually is to understand what does the Hilbert series look like and how is it related at a course level to the Hilbert polynomial. Okay. And we will make it precise, okay, when we get there. Okay. So recall that. So R is polynomial ring in over a field in some n variables, K field, and graded with degree of xi is 1 for all I and m finitely generated. Okay. Then there is a Hilbert series of m, okay, as a series, formal series, rank of mj as a k vector space times t to the j. This is what we have. Okay. So then proposition. What does the Hilbert series look like? Okay. So let D be the dimension of R, dimension of M. Okay. It could be less than n. Okay. Then there exists a Laurent polynomial. So we'll say what this means. Okay. So this means that something of the form over Z. So the Laurent polynomial over Z. Okay. So some ni t to the I goes from some n1 to n2, where n1 and n2 themselves are just integers. So for example, t to the minus 2 plus t to the minus 2 plus 5 t to the minus 1 plus 5 plus t squared, okay, something like that. So from some exponent n1 to some exponent n2, both of them could be negative, okay, or positive or something. They're just integers. Okay, so it's not a polynomial. That's why it's called a Laurent polynomial. And in this particular case, they are integers. So it's okay. So this is over Z, Laurent polynomial, which we will denote by q sub m of t. Okay, so the point is that there are only finitely many terms. It might involve negative exponents, but just only finitely many terms, such that Hm is Qm t divided by 1 minus t to the d. Okay, so what does this mean? So this one can be expanded as a formal, as a power series. Okay, so what does this mean? 1 minus t to the d can be expanded as 1 plus d times t plus minus d times minus d minus 1 divided by 2 factorial. This is to the minus d. Times minus t squared and so on. Okay, so one can expand it like this. So there are certain. So this can be written. Okay, so this is. So then Qm is a Laurent polynomial, finitely many terms. That times this will give. I mean, if d is positive, this will give an infinite term, and that is what Hm will look like. Okay, so this is just a. Sorry, just to explain what that notation means. And moreover, Qm of t is positive. We'll see a Qm of 1 is positive. We'll see in the next proposition what does it mean. Okay, this is the statement. Okay, so this. Okay, so let's just read it again. D is the dimension. Okay. Then it can be written as some Laurent polynomial divided by 1 minus t to the d. Okay, so we have to allow for negative things here because m could be non-zero in some finitely many negative degrees. Okay, so we have to allow for that. So we can write it like this. But this has the property that Qm is 1. So in other words, we can't factor out 1 minus t from this again. That's what it says. Because if this were 0, then we could put if this were 0, we could put, this would be QMT would be itself 1 minus t times something else, and 1 minus t would cancel one more term. So it says it cannot factor 1 minus t from it anymore. Okay, so proof. Okay. So proof is induction on D. On D. If D is 0, which means we are talking about a 0-dimensional module, so this now implies that after a while, so this says that Mj is 0, okay, for all j with all j sufficiently large and sufficiently small. Okay. In other words, if you write this sum, there are only finitely many terms in this one. Okay, so this is HMT. Okay, we can just write this itself, define this itself as QMT. Okay, it satisfies that condition, and QM of 1. I mean, this is the definition, so there is such a thing. QM of 1, remember, is just the sum of the these things. So it is the rank of M as a K vector space. That itself is finite because of this condition. Okay, so this is the D equals 0 case. Okay, so yeah. So the key point. Okay, we'll see. Okay, so D equals D is bigger than 0. Okay, so we'll address this in 2 steps. Okay. First, some special M, and then the general case will be reduced to it. There will be 2 ways to reduce the general case, and I will explain both. I mean, they are independent proofs. I'll explain both because they involve ideas that could be otherwise applicable. Okay? So, D greater than 0. First, assume that there exists some f in R, f in maximal ideal, homogeneous, that is a non-zero divisor on M. Okay. So we have done the following argument. Without loss of generality, we can assume that K is infinite. So this I will put. So this has to do with many problems in which we study about Hilbert functions. We can reduce this to this problem. Okay. So this is similar to an argument that we had used earlier, where we had a polynomial ring over K, and we had the polynomial ring in the same number of variables over K bar, and then we went back and forth using an argument. So with a similar sort of argument, one can also reduce this, that when we study Hilbert functions, etc., we can always replace K by K bar, for instance, and assume that it is infinite. Okay. Not all problems are okay where you replace K by K bar. There may be other ways where one has to replace and still get infinite. There are various techniques, but in this particular case, we can just take K equal to K bar. Okay. So this I will explain the exercises. It's a slightly longish calculation. Okay, so but if K equal to K bar, so notice that what do we mean by there's a non-zero divisor? This implies that, so this implies just this step. This step implies that M is not a subset of the union of associated primes. We observed earlier that the non-zero divisors are all in some associated prime. I mean, we use prime avoidance to a slightly stronger statement. The reason is every non-zero divisor, let's take, if F is a non-zero divisor, then the ideal generated by F kills something, and So that is contained in the annihilator of some element inside M, and maximal things with that property are exactly the associated primes. So therefore F is contained in some associated prime. Okay, so that's, and then conversely every element, P itself kills something, so every element of P is a non-zero, is a zero divisor. So to say that there is a non-zero divisor is to say that this is true. But now we use a K is infinite. Since K is infinite, okay, there exists, okay, so this is the slightly general form of prime avoidance. M is not contained inside M square union of the associated primes. Okay. In other words, we can find a non-zero divisor in M but not in M squared. That is a linear form. That is a homogeneous linear polynomial, sometimes called form polynomial. Okay, so therefore without loss of generality, F is 1, degree of F is 1. Okay, so now let's we want to consider multiplication by F. Okay, so if you take M and then map to M, multiplication by F, okay, some homogeneous some element M, let's say homogeneous, goes to F times M. Okay, so the degree of F times M is 1 plus degree of M. Okay, so in other words, this is not a degree preserving map. Okay. But we can do one thing, we can replace this by M minus 1. So instead of doing this, do this, multiplication by F. Okay, so now this is degree preserving. Okay. The element of M here would now live in the next degree. I mean, sort of artificially moving into the next degree, and then M will go to Fm, but M and Fm now has the same degree. Okay, so this is degree preserving. So we will keep this because remember, for it to add Hilbert functions to Hilbert series to add, we need we need degree preserving maps. Okay, so what is the Hilbert series of M minus 1? Okay, so this is rank of M minus 1 in degree j times t to the j. This is a rank of M j minus 1 t to the j minus 1, and then I put a t outside. Okay, but whether this is just j in z, whether we put j minus 1 here or j here, it's because we're the same, so this is just t times hm of t. Okay, so in general, if you shift the module degrees by some a, so if you replace m by m minus a, we would get t to the a. Okay, so that's what we have. Okay, so now we get, so from this short exact sequence, now we did this. This is multiplication by f. Okay, now from the short exact sequence, now it's degree preserving. Okay, we get from the short exact sequence of degree preserving maps, we get that t times hm of t plus hm mod fm of t equals hm of t. This is the middle one, this is the outer two. Okay, so from this we conclude that hm of t is hm mod fm of t divided by 1 minus t. Okay, and the degree, Okay, so we get this thing. So dimension, this we have checked earlier, dimension of f mod mf, m mod fm is dimension of m minus 1, which is b minus 1. Okay, so therefore h m mod fm is some q of m mod fm. This is the numerator Laurent series, t divided by 1 minus t to the d minus 1. And from here, if you just divide it by further 1 more minus t, therefore we get hm equals q of the numerator Laurent polynomial didn't change if you went modulo a non-zero divisor. Okay, and then so therefore qm is q m mod fm, and this proves that it does not vanish at 1, because by induction this doesn't vanish here, so this also doesn't vanish. I mean, by induction, if you substitute 1 here, we get something positive, so here also we'll get something positive. Okay, so this does the higher dimensional case, assuming that there is a non-zero divisor. Okay, so now let's get to this case. In general, okay, we want to reduce to this case. So we want to reduce to the case that there are two approaches, two methods. Okay, so method 1. So I'll do both because they're just sort of useful techniques that you might use it later or some other place. Okay. So suppose we have similarly n to n double prime to n double prime to 0. Let's say a short exact sequence of finitely generated graded modules of the polynomial ring with degree preserving maps. So hereafter I might just say short exact sequence of graded modules, and this will be understood that we will keep by default, we will shift these modules by some degree so that maps are all degree preserving. Okay, suppose. Okay, so we want to say that if we know it for n prime, and if you know the theorem for n prime and n double prime, then we will know it for n. How we will know it for n prime and n double prime is a different question, but let's do that. Okay. So if we take, so there are various quantities to be compared. So we want to express q. Okay, so what do we know? We know that, so let d prime be dimension of n prime, d be dimension of n, okay, and sorry, maybe let's use a different symbol. Let's call it e prime. So I have not yet used for m, so let's keep different symbols here. E double prime is dimension of n double prime. Okay, so what do the three Hilbert series look like? One, which will look like t over 1 minus t to the e prime. The middle one will look, we don't know what it is, but we are trying to prove that qn of t, we don't know that this is true, but okay, 1 minus t to the e, this is the expected form, and this we assume that the theorem is known for n prime and n double prime. E double prime. Okay. We know that the Hilbert functions are additive. This we saw in the last lecture. That degree preserving maps means that the Hilbert series of m. So therefore, okay. So let's assume that we know the theorem for n prime and n double prime. Assume that the result is known. This is not a correct argument because we have to check, we are doing an induction on dimension, so we have to check that dimension that is preserved. But right now I am just suggesting that if we can check that, how will we proceed? Assume that the result is known for n prime and n double prime. Okay. Okay. So then Hn of t will be the sum of the series on the outer two. So this will be Qn prime of t divided by 1 minus t to the e1 e prime plus Qn double prime of t divided by 1 minus t to the e double prime. Okay, and this is, so we have to adjust for the denominator, the exponent in the denominator. So we can say 1 minus t to the max of e prime e double prime. Okay, then depending on whether this is the max or not, it would be some 1 minus t to some a prime times q n prime t plus 1 minus t to some a double prime times q n double prime times t. Okay, where a prime is max of e prime e double prime minus e prime, and a double prime is the same quantity for e double prime. Okay, so we would need to adjust that so that the denominators are the same. So we get something like this. Okay, so now let's go back. Okay, so this is what we get. Okay, so now we can complete the proof if we know something about dimension. Okay, well, we know something about dimension, that dimension of n is equal to this number. Okay. And going back to the problem, so dimension of n is equal to this number. Then we can go back to it. Okay. So note that at most one of a prime, a double prime is non-zero, because we are adjusting this to get to the max, so only one has to be adjusted. Okay, so at most one of them is non-zero. So therefore, so we can rewrite, this is the potential candidate for n double Qn, and this is the candidate for dimension. Okay, so we'll keep this approach in mind. Okay, so note that. So we need to check something about. Note that the minimal primes of n prime is associated to n prime, which is associated to n. Okay. In other words, dimension of n prime is less than or equal to dimension of n, because dimension is length of a chain big from some such prime to a maximal ideal, and definitely that will include this is okay, because of this you get this condition. And n double prime is a quotient of n. Since n double prime is a quotient of n, dimension of n double prime is also less than dimension of n. Okay. Now min of m, remember dimension is always counted by something from here. So this is inside associated primes of m, and this is a subset of associated primes of n. Sorry, we're looking at this diversion of this new sequence n prime and n double prime, not the original m, union associated primes of n double prime. Okay, so this implies that dimension of m is less than or equal to max of dimension of n prime dimension of n double prime, because any chain from here must appear either in the support of n prime or in the support of n double prime. Okay. So in other words, our conclusion is that therefore dimension of n is the max of dimension of n prime, dimension of n double prime. Okay, so that we can actually use this thing here. Okay, okay, so therefore, okay, so once this is max, then this is the potential candidate for Qn, and okay, so then we can do that. Okay, so therefore, now we can conclude that Qn is equal to 1 minus t to the a prime Qn prime plus 1 minus t to the a double prime Qn double prime. Okay, and at most one of them is positive. So therefore, Qn of 1, okay, is also positive, because you won't get 0 on both sides. Okay. If a prime is positive, then you'll get 0 here, but you'll get 1 here, and so this is positive. Okay, assuming the statement for n prime and n double prime. Okay, so it's enough to prove the theorem for elements in for the outer two of a short exact sequence. So the conclusion is that enough to show that the theorem, the result holds. Result holds for the outer two modules. I mean, maybe I should be more precise. Result holds for a submodule of M, submodule and the corresponding quotient, of M. Okay. So now use a prime filtration. Okay, so we will get some Mi. This is inside Mi minus 1, and the quotient is some R mod Pi. Okay, we can adjust the degrees to make this a short exact sequence of degree preserving maps. So therefore, without loss of generality, and every module has a finite prime filtration. So without loss of generality, we can assume that M is R mod P for some homogeneous ideal, prime ideal P. Okay, but now there is a non-zero divisor on non-zero prime ideal P with positive dimension. Okay, I mean, if P is not the maximal ideal, R mod P has a non-zero divisor, and then we have reduced to the previous case, which we have already addressed. The case where the module has a non-zero divisor, we have already addressed. Okay. So another method. So this finishes the proof, but I just want to illustrate another method which goes in a slightly different, but still useful technique, which is the following. Okay. So suppose M has a non-zero divisor. Zero divisors. Okay. This implies that, sorry, that's not suppose. Suppose M does not have a non-zero divisor. Suppose M does not have non-zero divisors. Okay. This implies, this we observed earlier, M is in the union of associated primes. By prime avoidance, M is associated. I mean, M is contained in some associated prime, therefore M is associated. Okay. Okay, so therefore, there exists some x, some little m in M such that the maximal ideal kills it. This is the maximal ideal, that's the element equals 0. Okay. So now we can consider the following ascending family. Okay. What do we want? We want to take all elements, let me use y inside M, such that m to the n times y is 0. And this for n greater than or equal to 1. So if m to the n kills, m square or m to the n plus 1 also kills. So this is an ascending family. M is Noetherian. So write m sat for the stable value. Okay. So it has to be, every element in M sat would be killed by some high large enough power of M. So M sat is a finite length, submodule of M. Okay. And we will see saturation when we look at what is called projective geometry in a later lecture. Okay. So M sat is a finite length submodule of M, which okay, and moreover M mod M sat. Okay. So the maximal ideal is not associated to M mod M sat, because if this is associated, then there is something in this quotient which is killed by the maximal ideal. Therefore, something in M which is multiplied into M sat by the maximal ideal, but then that would have been multiplied to 0 by some even larger power of maximal ideal. So it would have already been counted. So M is not associated. So which means that this implies that M mod M sat has a non-zero divisor. So now we can use a thing. So we take this one, M sat. This is a finite length module. So and this is not equal to. So this is M, since dimension of M is positive. M sat is not equal to M. Okay, so the quotient is. Okay, so this is a finite length module. Its Hilbert series is just a Laurent polynomial. Okay. If you substitute t equals 1, we will definitely get something positive. We have M here and then M mod M sat. Okay. Okay, so the result is true for this. And then we can just write some Laurent polynomial and then use a sum value here. Okay. And if you substitute t equals 1, we will get something just. Okay. So in fact, you will see that when you work it out, Qm of 1 is equal to Qm mod M sat of 1. Okay. There is a reason for this, which we have not yet seen, which we will see in the next proposition. At least we'll see in the next proposition for ideals, not for all modules, but it's the same reasoning will apply also to modules. Okay. So this is the this is what we will conclude. Okay. Qm is not equal to this, but when you substitute 1, the contribution from M sat will go to 0 because of some terms. Because the Hm for this will have some denominator. We have to multiply the H for this. H of M mod M sat will have some denominator. You have to multiply by that. This is a Laurent polynomial. So you have to clear denominator. To make the denominators common, you have to multiply by a power of 1 minus t. So this won't contribute in this calculation. This won't contribute in this calculation. It will contribute to Qm, but not to Qm evaluated at 1. Okay, so that's the end of this proof. Yeah. So in the next lecture, we will look at some geometric applications called proj of a ring. Then use it to see some few cases of few basic situations of projective geometry we'll revisit saturation at that point. And then in the lecture after that, we will try to convert arbitrary non-graded situation to a graded situation, which also has a geometric meaning in terms of spec and proj. It has a geometric meaning. And there are certain advantages of working with in the geometric, in the graded case. Okay, so we'll try to discuss them in the next 2 to 3 lectures.